Hey there, college algebra folks, back here to look at just a few more examples coming from section 5.5, where we're going to focus in on, here in this case, solving some exponential and logarithmic equations. You can see here I have 4 examples planned, where 2 of those examples are solving these exponential equations, and 2 of these examples involve solving some logarithmic equations. And one of the big ideas we rely on is we certainly rely on those properties that were that we saw appear in the last section of material, where we were discussing logarithms and looking at examples of logarithms in our work. But there are 2 other quick properties we do take note of, and that is we might say something along the lines of b to the nth power equals b to the nth power if and only if, we saw this statement IFF used last time in the notes, right? If and only if the value of m equals the value of n. This is known as the, if we give this a name, this is known as the exponent property of equality, right? Which allows us to say that an exponential equation, in an exponential equation, if we can write both sides of the equation with the exact same base, right, value, that value of b, then what we can say about the exponents is that the exponents must be equal. Or similarly, what it allows us to say, and this is what is unique about an if and only if statement, this works either way, is that if I have 2 bases, right, the value of m and the value of n, if I raise those up to a higher power, or if I make those a power of some common base, that those statements would be equivalent. All right? This is known as the exponent property of equality. We can use that to solve this equation here, right? By noting, is there a way to rewrite either one of the bases on either side of the equation so that it resembles the base seen on the other side? And what we might note is that here on the right-hand side, with respect to the value of 9, right, that can be rewritten, right, as the value of, if we leave the left-hand side alone, we can rewrite the right-hand side as the value of 3 squared raised to the power of 2x. Right? Where I've taken the quantity of 9 and expressed it here as the quantity 3 squared. Because we know 3 squared is equal to the value of 9. Now, here on the right-hand side, having this power of 3 raised to this higher power of 2 to the x, right, or 2 times x, what we can do there on that right-hand side is write it with just a single power. If we remember our power rules here, we can multiply those powers. Remember the rule, if you have b to the nth, and that's all raised to the nth power, this is the same as b to the m times n power. All right? We're going to apply that exponent rule here on the right, and that's going to say we're going to have 3 to the 2 times 2x power. That would be 3 to the 4x power. Where what I have here now is a statement very similar to our property of equality here, where I have the exact same base on either side of the equal sign, which must imply then, if I think about these 2 values for the powers, right, these 2 values given by these exponents 1 minus x and 4x, those must be equivalent to each other, right? 3 to the 1 minus x equals 3 to the 4x if and only if 1 minus x equals the value of 4x, which now is just a linear equation. A linear equation we can solve by adding x to both sides. That will say that 1 equals 5x in value. And then continuing to solve for x, we can find x is equal to, divide 5 on both sides, x is equal to 1/5 in value. Or we might say we're going to multiply both sides by 1/5. All right, and that leaves me with x equals 1/5 in value. Now, certainly we may want to check that, right? Here on the left-hand side, that would produce 1 minus 1/5 is 4/5. And similarly here, I'd get a power of 4/5 on this right-hand side, right? 3 to the 4/5 power must equal 3 to the 4/5 power, right? It does check. And I will tell you, for most cases, if you work the algebra correctly, these will check for you. It's logarithms you really do have to be cautious of, right? If we look at another example, we might consider this case here, right? Or if you start to consider that case there, that second case, right? In this second case, there really is no way to rewrite the value of 75 as a power of 5. It is 3 times 25, where 25 is a power of 5, but that doesn't quite get me to what I need here to be able to apply that property of equality. So what I'm actually going to rely on here, folks, just a different way to go about solving these problems, and what we're seeing here is a couple different examples, is we can apply the idea of a logarithm here. All right? We can rely on the idea of a logarithm. If we go back to logarithms, we had that fundamental idea that said, what was it? B to the x power equals y, if and only if, what's true? Well, that would be that x equals the log base b of y, right, in value. And here we have this exponential statement equal to this value on the right-hand side. Looks very similar to what we have going on here in our understanding, right? B to the x equal to y, and that must be true then if and only if we have this be true about that statement. And what would be correspondingly true here is that the quantity 2x minus 6, the power from this exponential statement, must be equal to the log for the base of the exponent, which in this case would be 5, applied to the value of y, where y was this value we were equal to on the right-hand side. Right? Our value, 2x minus 6, must be equal to the log base 5 of 75. And what is the log base 5 of 75? Well, that is itself, if we go into our calculator and remember how we calculate that, we can use a little change of base. That would be log of 75 divided by the log of 5 using the change of base formula. And it's about 2.682606194 in value, right? We get this bit of an irrational value. I don't really see a pattern forming in there, right? Where the best way to write that irrational is using this log statement. So from here, to solve the remaining portion, we do have this linear equal to this logarithmic value, where we apply linear properties. We add 6 to both sides. So I'm able to say something like 2x must be equal to 6 plus this irrational value given by the log base 5 of 75. And then we divide 2 on both sides, or you could say we multiply by a half on both sides. And make sure when you multiply by a half on the right, you distribute. And you're left with here x equals, when you distribute to the 6, that will become 3. And when you distribute to the log, that will become plus 1/2 log 5 of 75. All right? That is your exact value for x. If you were to plug this back into your equation here, right, and simplify that statement, you would see that the 2 times this entire quantity would make this 6 plus, and the 1/2 would cancel here, log base 5 of 75. When you subtract 6 from that, the 6 will go away. You'll be left with just the log base 5 of 75. And what is 5 raised to this power? Well, the power and the log cancel with each other, leaving behind just the 75. And 75 would equal 75. It does check, folks. All right? So that's 2 quick examples that involve this property, right, of equality. which we learn about in section 5.5, or also involves some of the other properties we've established for both logarithms and exponents. I'll be back in another half to this video where we'll look at solving these two logarithmic equations. I'll be right back. Hey there, college algebra folks, back here with the second half to this quick video where we're looking at solving exponential and logarithmic equations. And we have a couple more problems to look at here, right? This first case, the log base 2 of x plus the log base 2 of x minus 2 equals 3. We're interested in solving that logarithmic equation as well as solving this one down here. The log base 5 of 6x minus 3 minus the log base 5 of 2x plus 2 must equal the log base 5 of 7. All right, these are just two logarithmic equations, right? These are two equations that involve logarithmic expressions that we're being asked to find the value of x in these equations that make the equations true. All right, we might start here with this first one, right? And again, what we're going to see here in this first one, we've actually seen this property play a role already in our notes from the previous section, where we can take these two individual logarithms that are being summed together on the left-hand side and consider rewriting these to make or produce one logarithmic statement, right? If you recall, there is that logarithmic property that says if you have the log base b of m and you add that to the log base b of n, that is equal to the log base b of m times n. We can rewrite this logarithm as a single logarithmic statement by applying this property. So if I apply this property down here, we're dealing with logarithms of base 2. So this is going to turn into a logarithm of base 2 as a single logarithm, where with those arguments of the logarithm, I'm going to want to multiply them together inside the argument of the single logarithm. I am going to want to take what represents m, take what represents n, and form what is going to be m times n, this quantity down here inside this logarithm. Where if I do a little expansion, you will see this does turn into the log base 2 of x squared minus 2x. All that must equal the value of 3. Where to go forward now, this does look, well, I should say this does maybe look a little familiar to you. We have to kind of try to figure out how are we going to isolate these values of x seen here inside this argument. And what we're going to do is go back to and rely on that idea that if, well, let's not start it with an if, let's say it this way. The log base b of y equals x, if and only if b raised to the x power is equal to y in value. All right, we're going to go back to that fundamental understanding of a logarithm to help us solve this. Because I do not have a logarithm on the right-hand side, what I can do is apply this idea and consider rewriting it as an exponential equation. So if I apply that idea to this statement here, again, our base is the value of 2. This would be 2 raised to what power? Well, that would be x. That would be whatever by itself on one side of the equal sign in this logarithm. That would be the value of 3. Must all equal then what is the argument of this logarithm, right? It must all equal y, which is the argument of this logarithm. So that would be equal to x squared minus 2x in value. And if you spend just a moment cleaning that up a little bit, finding 2 to the third power, you will see this equation develop. And remember, folks, this is, you should recognize, is a quadratic. That is a quadratic equation where to solve this quadratic, we have to begin by setting it equal to 0 by subtracting that value of 8 from both sides. Once set equal to 0, we can now attempt to factor it if it factors. And I do believe this case does factor into x minus 4 and x plus 2. You will see that gives us x squared minus 2x for the middle term, and then minus 8 for the last term, so that does factor. Where to finish off, we apply the zero product property with each of those factors and find x is either equal to 4 or we find x is equal to -2 in value. Now, I will warn you folks, you do have to kind of go back and double check these values in logarithms. We are going to want to go back and double check that in our equation, plugging in for these values of x, these values. And I should be careful there circling those. Notice if we plug in 4, the log base 2 of 4 is 2 in value, and the log base 2 of 4 plugged in here would be the log base 2 of 2 in value. That would be 1. You will have 2 plus 1 equal to 3. So the 4 does check. All right? That one does check as a solution, and I do caution you to check your solutions in the case of logarithms here, because not every solution will work. We've actually encountered what we might think of as here as a pseudo solution, a fake solution. If I come back up here and I try to plug in the -2 here, that'll be the log base 2 and -2. If I plug in the -2 here, that would be the log base 2 and -4. And what we have to remember about logarithms is that that argument plugged inside here, those arguments always have to be greater than the value of 0. This argument of x seen here has to be bigger than 0, and this argument x minus 2 given here has to be bigger than 0. And if you go back and recall, when we plug in the -2, this is negative in value, right? And when I plug in the -2 here, this becomes negative in value. These conditions are not met with this solution of -2. So that is actually a pseudo solution. That is not a solution to our problem. And only x equals 4 becomes a solution there, folks. All right? So again, that is solving logarithms. That's one style of problem you might see there, where you have to apply some properties to write it as this single logarithm, and then once written as the single logarithm here, equal to this real number on the right-hand side, typically applying this identity or this idea of what it means to be a logarithm is what allows you to move forward in that solution process. Here it turns it into this quadratic equation that we can solve. All right? If we look at another quick example, we might look at the second case here, where again we might start off a little like we had to begin with here. We are going to, in a sense, take this logarithm on the left-hand side and rewrite it as a single log. And if you remember those powers, we said the log base a of m, or these log rules, I should say, minus the log base b of n is always going to be equal to the log base b of what is m divided by n, right? We're going to apply that property here on the left-hand side, which is going to allow me to rewrite this as a single logarithm, where the base of that logarithm is the base we see given in the individual logarithms that we're combining. That would be a base of 5, where we now want to take the arguments of these logarithms, take the first argument in this difference, and take the second argument in this difference and form them into this ratio, using the first argument of the logarithm in the numerator and using this second argument of the logarithm down here in the denominator. And what this becomes is the log base 5 of 6x minus 3 over the quantity 2x plus 2. And all that must equal the log base 5 of 7 on the right-hand side. Where, to go any further with this, what we might consider now noting is that there is a property of equality. There is what we call the log property of equality, right? Where you will notice we are taking a logarithm on the left and saying that it must equal this logarithm on the right. Well, a log base b of m will equal a log base b of n, right? If and only if what's true is that the m is equal to the value of n. So if I apply that property here in this case, that means that what we have here in the logarithm's argument on the left, 6x minus 3 over 2x plus 2 must equal this logarithm's value argument over here on the right, must be equal to 7 in value. And notice what we prepare here, folks. This is a case for a rational equation. And we should be familiar with how to solve rationals, right? We covered this earlier in the semester. We are going to want to multiply both sides of that equation by a common denominator of all denominators. Notice the common denominator of all denominators is 2x plus 2 times 1, which is just 2x plus 2. That's convenient here on the left because they will cancel, leaving you with 6x minus 3 equal 2. And on the right here, we're going to have 7 times 2x plus 2. Now, you may or may not see it, but this is a linear equation at this point. To continue solving the linear, we will distribute the 7 on the right. This will become 6x minus 3 equals 14x plus 14. We'll go ahead and consolidate all the values of x maybe on the right. We'll subtract 6x from both sides. We might move the constants over to the left by subtracting 14 on both sides. And we will find here negative 17 must be in a sense equal to the value of 8x, or that x must be equal to negative 17/8 in value. Now, before I circle that, I ought to go back and check it, right? With logarithms, you do want to check these values. You'll notice this, if I plug in negative 17/8 here, when I multiply that by a 6, it's still going to be negative, right? When I multiply that by a 6, it'll actually become something like what? Negative 51 fourths, if I'm not mistaken. And then when I subtract 3 from it, it's still going to be negative. So this very first logarithm, when I plug in negative 17/8 into it, it does remain negative. We produce a negative result inside of here. And because it produces a negative result inside of here, that cannot be a solution to this argument. In this case, this logarithm has no, what we might say is real solution, right? This case has no real solution because the value of x we found in our solution process, right, is negative in value, and it does not check, or when we come up here to try to check it, it's going to produce a negative argument inside this logarithm. And similarly, it'll also produce, I believe, a negative over here, right? Negative 17/8 times 2 is negative 34/8, which is negative 4 and a fourth, but when you add 2 to that, you still get another negative value. So it also doesn't check here. It's not going to check here or here, right? So this cannot be a solution to this equation. And since that's the only solution we encountered algebraically, there must be no real solution in this case, folks. All right? So that's a couple more examples here on solving logarithmic and exponential equations, folks. We looked at these 4 examples here, and I think these 4 examples, as well as some more practice in the book, will all give you some good illustration as to how to go about solving some different types of logarithmic and exponential equations. You are going to want to rely on your properties of logarithms, right? We relied on a couple of properties of logs here. For instance, we relied on this sum property in this case, and we relied on our difference property in this case, as well as at times you may have to rely on that fundamental understanding of a logarithm, right? And exponents, how they relate to each other, as well as maybe some properties of equality, right? For either our exponential or our logarithmic equations. And along with that, you are also going to encounter some other properties of exponents that you may have to make use of at times, as well as, do I have any others on here? Oh yeah, some exponential properties of equality, right? So make sure that you are also studying your properties, folks, here for exponents, which is actually review material. That's stuff you should be coming into this class aware of from Math 116 or your intermediate algebra studies. it's the logarithmic properties that are really the new properties here. Those are presented in the section before here. This material, I think this is section 5.5, so that would be presented in 5.4, and I went through some of those properties in the last set of notes in my last video, and then I also am seeing a few of those properties come back into play with these examples from 5.5 material. All right? So, again, folks, study your properties. Be familiar with your properties of logs and exponents. It's these properties that help us solve, right, these equation types that we're going to encounter. Right? As well as our skills in solving other equations. Don't forget how to solve quadratics, or how to solve rationals, or how to solve linears, or even radicals, right? We've looked at solving a lot of different problem types here. Right? And you need to be familiar with those as we go into this last test here, or this, I should say, a fourth test for this semester. And I'll have that test posted up for you shortly, folks. Look for it along with this video going up very soon. So I hope you're all doing well. I hope you're all hanging in there. I've seen a few of you. I haven't seen quite as many as I've hoped, but I hope that you're all doing well, and that we can get through this semester together, folks, and get you off and on your way into your future studies. If you're having struggles, though, make sure that you're getting a hold of me, that you're dropping in during those collaborate times. I am more than happy to help. And with this next test going out, you folks may be looking for some help, and certainly use your time wisely and jump in there and see me when you do have those questions. Other than that, folks, I hope you're all doing well, and I'll see you in the next video. Talk to you then.